you go. Okay. Everybody took the quiz yesterday, right? I have 2 remote students taking it today. I didn't have a chance to grade those. I just didn't get it yesterday. I just didn't have a chance to do it. So what I thought I would do is I'll grade those, and maybe I'll have those done by tomorrow, and you'll be able to see them. But I just want to know, before we go on, is there one of them that you thought, well, I don't know about that. That's the one I didn't expect, or that's the one that I didn't know how to do that one. What do you think? This one.
Number 5.
Okay. Now, I put in there, that one is, it does make you think a little bit. It's kind of like a problem solver. And so let's take a look at it. It says here, what mass of NaOH is required to neutralize that? You did not have to use the acid-base neutralization equation. You did not have to. I could write this equation out, and it says here, NaOH is going to react with HCl, and what's it going to make? What's it going to form? Okay, some kind of a salt. In this case, it happens to be the world's most famous salt. Right there. Now, and it's already balanced, isn't it? That was good news. It's already balanced and everything. Now, it says here, what mass of NaOH, so you want this is what you want me to find, 25 milliliters of 1.2 molar HCl. Okay, so let's say I'm not going to use the equation. I will. I can show you how to do it. But how would we do this? What is molarity times volume in liters? What is molarity times volume? And whenever I see a problem, you can give me the volume, and you're going to give the molarity. Ding, 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 ding. I'm going to get in the mole world right away. So we have 0.025 liters times 1.2. All right, somebody help me on the calculator. What is 1.2 times 0.025? Say it again.
0.03.
Is that right? That's zeros? Okay, yeah, it would be zeros. I guess it would be. Wait, 1/4 of that? Yeah, you're right. That is 1/4. Okay, does everybody get that? So now what? If I'm going to go here, then is that right? Is that what it looks like? But it says what mass. And so how we do that? Wait, now divide. When you're going to go down the mole world, you divide. Yeah, multiply, right. And everybody know by now, a lot of chemistry people know the molar mass of water is 18. What's the molar mass of NaOH? 40. And so what's 40 times 0.03? How much? 1 point what? 2. Yeah. Oh, 4. That makes sense. Is that what you got? Something like that? Now, what if you had used this equation here? What if you had done this? You said, I'm going to use this equation. It's neutralization. Now what? All right, what numbers do you know? I know this one. I know 1.2 here. And I know this one. And that's 25 milliliters. Or 0.025 liters. And, what happened then? How am I supposed to get those? And so the other day I asked you why these equations worked. Why does the dilution equation work? Why does this one work? What does molarity times volume equal? Moles. So if I were to multiply these, what would it give me? It give me this, but what does this equal? Moles of OH, right? Which is NaOH in this case. So then I could actually have used this equation to find moles of NaOH and then change that to grams. Or I could have done the way you've been used to doing it. All right, what else? One more. How about one more? Did you get this one? Yeah.
Yeah, I was going to say the last one on number 6.
Let's do the last one. I just need a little help here because I have I worked it out, but it's in my paper. 500 milliliter solution of 3 molar aluminum sulfide. So that's going to be like this. Wait, that's going to be this, right? Was prepared in a 10 milliliter sample of this solution. What's the concentration? Okay. All right, so what do you think?
3 molar?
It is. Any amount of that is 3 molar. what is the concentration of aluminum ions? Ooh. For every one of these, there are 2 of these. So what's this going to be? Okay. And what is the concentration of sulfide ions? For every one of these, there are 3 of those. What's that? 9 molar. And how about I didn't ask it, what about the concentration of total ions? For every one of these, there's 5. Is that right? So 5 times 3 is 15 molar ions. Okay, then it says, and by the way, this doesn't matter, did it? This didn't matter yet. It didn't matter as far as these answers, did it? That didn't matter. Now it matters. In a 10 milliliter sample, how many moles would it be? And you said what? What's that equation? Right? Is that right? Okay, so what's the molarity? And what's the volume? All right, there we go. And so what's that give you? Is that right? Yes?
Since it's moles of total ions.
Oh, wait. You know what? I just made a mistake. Okay, sorry. I thought it was asking for moles of aluminum sulfide. I just made a mistake. Sorry. Thank you. So let's try it again. What is the molarity of the total ions? For every one of these, there's 5. 5 times 3 is 15. So, my fault. So it's really 15 molar. When the concentration of ions is 15 molar times 0.01, what's that give you? Wait, 100? Is it 0.15? Is that what you got? Okay. All right, what do you think? You okay with that? All right, well, I'll try to get all those graded and try to give those back to you tomorrow. There's that one. Now, what I want to do today is take a little bit different route. Instead of doing stoichiometry and mathematics, I would like to do something that an advanced class should be able to do. I'd like to look at some material, have you read a little bit, and then discuss it. I want to ask you to discuss some things. And so I'm going to get my book out. Oops, that's wrong book. Buried it. There we go. All right. In the original packet that I gave you, it told you that this chapter, no, not that one. Here it is. It said that this next test is not just on this chapter, is it? This is on this chapter plus some additional readings. Now, the additional readings are page 330 to 338, and pages, and some of these are actually in the chapter themselves. But I'm gonna go to, let's go to page. Let's see what's on 330. Oh, wait a minute. Wait. Sorry. All right, sorry, not yet. Almost. We're almost there. Let's go back to a story that I told in the 10th grade, and I also told a little bit of this story in the physics also. And let's see if we understand this a little bit. This chapter is on solutions. The most common, as a matter of fact, they call it the universal solvent, is water. Water does not dissolve everything. It dissolves a lot of things. And so, what is it that makes water able to dissolve so many things? Okay, do you remember some of this?
The molecule itself is highly polar.
Right. Now, in the 10th grade, I would have just told you that it was a polar molecule, and I probably explained a little bit how that works. So I'd like to go a little more detail in that with you guys. You're advanced. So let's take a look at the water molecule. The water molecule is made of one O and 2 H's. Is that correct? What kind of a bond would you expect to form between these two elements? What is it? Ionic? Okay, now, why would you say ionic? But let's think about this, because oxygen and hydrogen are both called nonmetals. They're nonmetals because what do they like to do with electrons? Wait, let's think about this. I'm not hearing the same answer from everybody. Metals like to have the tendency to lose electrons. Maybe they lose 1, 2, or 3, and they become cations, don't they? Why do they become positive ions? Because they lose negative things, don't they? Nonmetals have a tendency to grab a hold or steal people's electrons and become extra negative. That's called an anion, isn't it? So if I had a metal and a nonmetal come together, it would kind of make sense that the metal would lose electrons and the nonmetal would gain them. They both become ions. And why can't they get away from each other? What do you call a bond between ions? Well, ionic. And an ionic bond is formed between ions. And what's an ionic compound made of? Ions. And what is it made of before I put it in water? Ions. So what happens when I put it in water? Water has the ability, not always, to overcome those forces and dissociate the ions. Is that correct? And now we have a solution that has full of ions, right? And what do you call a solution that can conduct electricity because it contains ions? Electrolyte. And Powerade, electrolyte. Doctor says, hey, they got a fever? Give them some electrolytes. What's that? You can go to the store and pay a whole lot of money for Pedialyte. Pedialyte looks like water, but it has a bunch of ions in it. Or you just give them some Mountain Dew, or you give them some Coke. That has electrolytes in it. Yes.
So, what about the ions makes them able to conduct electricity?
Okay, now what I should say when I say conduct it, it actually carries a charge like from one side to the other. So that's something I'm not sure I've ever studied. Is what is it about an ion that says I can carry extra charge with me? What makes me able to conduct electricity? That's a great question. I don't think I know the answer right now. Let me think about it. Why does an electrolyte, if somebody says, why does electrolyte conduct electricity? They'll say, because the ions carry the charge from one side to the other. Well, how are they able to do that? That's a good question. Yes?
How do electrolytes help? Like, if you have a fever, like, what do they do?
Believe it or not, your body, it's a lot of water, right? And God is pretty smart. The whole thing is just so smart. And have you ever thought about this? You had a biology class, so you know this. Did you ever think about what happens in cells when, let's say, I touch something and my brain makes my hand go like that? All these nerves, right? I have nerves in my head, on my brain, and they're all working on electricity. You say, what the heck? I'm not even plugged in. How are my nerves able to run on electricity? I did this. Please don't do this at home. But when I was little, remember trying to get a piece of toast out it's stuck in a toaster, Please don't do this. And you touch that little thing. Don't do it! And your whole arm just it just contracts, doesn't it? So you set off all these nerves that made the muscles contract. And all these nerves and muscles operate on ions. Ions, if you can make the cell membrane say, push those ions out, push this many ions out and this many in, all of a sudden I'll become charged. And if you have a charge set up in a nerve in about a thousandth of a second, you can actually set up an electric charge that'll go from one end to the other. And then there's a little gap between one nerve and another. Remember, it's called a synapse. Have you ever heard that word? Okay. The body fills that little gap with some kind of neurotransmitter, acetylcholine maybe, and goes, pooh, pooh, and it goes to the next nerve, next nerve. See? Okay. So all of your nerves work on ions being moved in and out of the cell, and your muscles the same thing. Even your muscles contracting, it's ions being brought in and out of the cell. And so, electrolytes contain ions. That's what I want. I want all these ions in here because if I have a fever, I'm losing a lot of water. And a lot of times, if I get sweat that comes out, do you ever see how it gets kind of crusty or salty? Right? Those ions are not in your body anymore. They're on top of your body, aren't they? So you could be dehydrated in the summer pretty easily if you don't keep, replenishing at least the water. I don't know if I answered your question of it. The more you look into it, the way muscles and nerves work are ions being pushed in through the membrane, out in, and so that's why you need electrolytes, okay? All right, well, let me go over here, and let's look at this picture again. Now, we started off poorly because I asked what kind of elements were hydrogen, oxygen. Everybody should have said non-metals, shouldn't they? Now, if a non-metal and a non-metal, if they want to form a bond with each other, I want to gain. I want to gain. No, I want to gain. No, I want to gain. Well, how in the world can we form an ionic bond if both of us want to gain? You're right. That is not going to happen. You're not going to form an ionic bond between a non-metal and non-metal. But you could form a different kind of bond, a covalent bond. In that case, they can both gain at the same time, not by transferring electrons or stealing them, but by sharing them. And we believe electrons are moving at high speeds, speed of light almost, and we don't even know where they're at. If I thought you were there, you're not there anymore. Oh, you're right there. No, you're not. No, they're all over the place. You could share electrons like that. And just like I did in the 10th grade, though, when I say share, I know what you're thinking. Here's a candy bar. Is it okay to share? Sure. You think I mean cut in half and give you... No. I'm going to cut a little piece off and give it to you. I'll eat the rest. And what are you going to say? Did I share? I did. I did share. And that's what happens in the chemistry world. You think sharing means equally? No, not always. So we have this saying. I didn't answer your question. Go ahead.
I was going to ask, can't hydrogen also give up an electron?
You are correct. Now, even though that's not my discussion today, you are absolutely correct. Because the first energy level can only hold 2 electrons, and hydrogen has 1. It can gain 1 and fill it, or lose 1 and empty it. Same thing happens with like carbon. Carbon is number 4, has 4 valence electrons, but 8 is how many it takes for the second energy level. It could gain 4, and it could lose 4. So in this first level, the magic number is 2, and if you're halfway there, you could do either one. In all the other levels, it's 8, and if you have 4 valence electrons, you could go either way.
Does it not really form bonds once it loses an electron?
Okay. Now we have to be careful because if you lose an electron, become an ion, then you have the tendency you could form an ionic bond with something, yes. But if you're going to gain electrons with something else that gains, then you're probably going to form a covalent bond. Okay, yes?
Sorry, so if there's 2 different bonds, which one is stronger? Because I remember learning about like ATP and how there's the
Okay, so we're getting into that today. All right, so what we're going to do is, the story is not as simple as I did it in 10th grade. It's a little more complicated, okay? So here we go. What kind of bond is going to form between hydrogen and oxygen? Covalent. Now, I had given you this yesterday, and it's in your book too, but I had given you a special periodic table that had a set of numbers on it, and they were called electronegativity numbers, okay? I think some of you are going to like this a lot because it's going to answer some questions that I probably couldn't answer in the 10th grade for you. In electronegativity, I didn't make up the definition, but the definition says, what is that element's ability in a covalent bond situation? What is its ability to pull the electrons toward it more than your ability to pull it towards yourself? You might say, how greedy are you? If you're going to share electrons, to what degree are you going to have them come over to you? If you like the Snickers bar and you cut off 90% of it, you're a very negative if you're at that level. So let's take a look at these numbers. Now, again, I don't know if you can see them well or not, but does anybody see, what do you think, where's the highest electronegative element on the periodic table? What's the highest number you see for electronegativity? Anybody found it yet?
Fluorine.
That's it. Okay, here we go. So let's focus over here. Fluorine is known as the most active, most chemically active nonmetal. It has the highest electronegativity of any element in the nonmetal, in the whole periodic table, actually. If you put fluorine next to any element, it will have a tendency to grab a hold and steal your electrons. Now, find the one that has the lowest electronegativity numbers.
That would be francium.
All right, francium, okay. Anything down in this zone, right? What is that number? 0.7? What is francium's tendency to grab a hold of your electrons? Like nothing, almost nothing. Okay, real quick, and I gotta keep moving.
I was just gonna ask why krypton, xenon, and
Okay.
uranium
Excellent question.
have such,
The test that they used, whatever equipment they used, at that temperature, all these elements called noble gases, what did they like to do with their electrons?
just
Whatever they have, they have to hang on to, right? Do they want extra ones? No. So they have no electronegativity. The tendency for them to grab a hold of my electrons is like 0. That's why we say they're chemically inactive. Now, can I force them? Can I heat them up to 5,000 degrees until electrons are coming away from them? Can I make them react? I can. That's not normal. Normally, they're very inactive. Now, take a look at this. So the nonmetals tend to have high electronegativity numbers. That makes sense because nonmetals like to gain electrons, don't they? And the metals have low electronegative numbers. They don't have a tendency to gain electrons. They're trying to get rid of some, aren't they? And so for the first time, I'd like to show you what's going on here, right? It's not black and white, ionic, covalent. Let's take a look, and I want you to ask, what would happen, what kind of bond would form between hydrogen and hydrogen? If I formed a bond between hydrogen and hydrogen, we'd call that compound H2. All right, what kind of a bond would form between them? Here's how you do this. You look for difference in electronegativity. This right here says electronegativity differences. All right, what's your electronegativity? I can't read that number. What is it? 2.1? I'm 2.1. What are you? I'm 2.1. What is the difference in electronegativity between hydrogen and hydrogen? 0. Let's go down here. If you have 0 difference in the electronegativities of the two elements, it is 100% what kind of bond? Covalent. There's nothing, no. There's no tendency to become ion. Nope. Let's try another one. Let's try sodium and chlorine. What is the difference in electronegativity between sodium and chlorine? 0.3. Is that 3.0?
yeah, sodium is
All right, so what's the difference in electronegativity?
sodium is 0.9.
I'm sorry, what is it?
Sodium is 0.9.
Oh, oh, 0.9. Sorry. So what's the difference?
2.1.
Okay, let's go down here. And what if your difference is 2.1? You're way up there. As a matter of fact, I don't know why, but some books hesitate to put the number here. I'm going to look it up in a couple of the books, but there's usually a number here, and it's around 1.7. It's around 1.7. I'm going to look it up because some books don't even put it on there. I think they don't want to commit to it, but when you get past this certain point, you are so ionic. And I'm not going to say 100% ionic because essentially nothing is 100% ionic. But you're so ionic. Okay? But now let's take a look at water. Let's do water and do the hydrogen to oxygen bond. The hydrogen to oxygen bond, what would you expect it to be? What's the difference in electronegativities? 2.1,
Is this, do you subtract?
2.5? What do you think? 0.4, is that right?
So it's just between.
So it's not,
Type of element, it's not the amount of each element in it.
right, it's the difference It's,
Oxygen is 3.5.
ah. Can't read well. Okay, 3.5. Is it 1.4 difference? I'm up there. Now, even though in 10th grade I would have said covalent bond, wouldn't I? Now we know it's not truly covalent. It actually has tendencies. We can say covalent, and again, I think the 1.7, I'll look it up, but we know that you are covalent, but we now know that if you're not pure covalent, you are what they call polar covalent. Polar covalent means that when they start sharing those electrons, one of those elements is going to pull those electrons on that him, and it's going to spend more time around him than you. And so here's what's going to happen here. Look over here. Here's oxygen, here's hydrogen. What kind of bond forms right here? A polar covalent bond. Where are the electrons going to spend more time? Between here or here? Here or here? Oxygen, right? Now, what charge do electrons have? Okay, so I have extra, my own electrons, plus your electrons are spending more time around me, aren't you? And so we see this little funny symbol, and I wrote on mine, sorry. Do you see where it says this little weird symbol? That means partial. It's a partial negative charge. Everybody see that? Now, it's not a full negative charge. It's partial negative charge. You get it? It's not like, you couldn't say -1. But it's a partial negative charge. But what happens over here? What happens at the hydrogen end? What's that little symbol mean? Because I'm lacking in electrons, aren't I? And so I tend to become slightly positively charged. Now, in the 10th grade, I would have said this. That's why it's a polar molecule. One end is plus and one is minus. The story is actually a little bit more complicated. So let's go back to physics. Let's go back to physics. Do you remember the vector world? Let's do the vector world, okay? Ready? What's this vector plus this vector? That vector. What's this vector plus this vector? What's this vector plus this vector? It's that one, isn't it? All right, here we go. What kind of bond is right here? Polar covalent. I'm going to draw an arrow toward the element that the electrons spend more time with. You see a little arrow I drew here? Okay. This is called a dipole moment. We're going to read about this later. There's a dipole moment right here. And that says they're going to spend more time towards you. But the story's not done yet. Now we go over here. What kind of bond's going to exist here? Polar covalent. I'm going to draw the arrow toward him again. Ready? Now, that tells me what each bond was, but it doesn't tell me the molecule. Now, tell me the molecule. Will the molecule be polar? The bonds are, but will the molecule be polar? Now watch, ready? What's this plus this? That. And now we know, the final story is, the entire molecule will end up being polar. There'll be what they call a net dipole moment, meaning that this end will tend to be negative, this end will tend to be positive. Now, I don't want you to misunderstand this because if I don't do it today, I could get a situation where the dipole moment goes this way and the other one goes this way. They're both polar covalent bonds. But what's the molecule going to be? Polar or nonpolar? It's going to be nonpolar. And so that story it is a little more complicated, but let's go back to our water thing, okay? We now know that we have a polar molecule, don't we? Okay, so one more time. One of the questions I asked on the next test, describe the intramolecular and intermolecular bonding in water. Okay, let's try the first one. Intramolecular means I'm only looking at one water molecule, isn't it? What kind of bonding is there intramolecular? And polar covalent bonding, right? And two of them, right? What is the, which sets up a polar molecule, doesn't it? What is the intermolecular bonding in water? Intermolecular? You mean between one water and another water and another water? Okay, so let's take a look down here. What would happen if I put a water and I put water next to water next to water? There's an additional bond which occurs. It's not called covalent. It's not called ionic. Anybody know the name of this one? Hydrogen bonding. Ooh, you did that in biology class, didn't you?
I think we talked about it.
We did. Anyway, this is called hydrogen bonding, and this is so important. And so what happens is, if this end of the molecule is slightly negative and the hydrogen is slightly positive, there's going to be an additional attraction there, right? And I'll show you later on another chart. If you were to take 100 molecules that were the size of water, about the same mass, and you ask me what temperature would it boil at? You take this other guy who's not polar, and you heat him. If I heat him, gas, I change to a gas. At a low temperature. Next one, little guy, change to a gas, pretty low temperature. Water, higher. Okay, now I'll change to a gas. Water has a boiling point much higher than it should have. There's something that keeping it from boiling. What's keeping it from boiling like the other guys that are non-polar? Hydrogen bonding. Now, I know you think that doesn't sound real important, but that's actually the key to so many things that you see on the planet. It's the key to life on the planet. God, I just think, at one time I didn't think much of it. I thought it was science, but the more I think about it, I look all the way through the solar system. Where's water, you know? It's not just everywhere, is it? It's here. And I look at living things here, and I think, there's a lot of water in living things. Not too much water here, but water's not that important right there. Water seems to be important to living things, doesn't it? And we have a lot of it. Wow, that's a nice place to live. I need water. Water's very important, and I live in a planet that has a lot of water on it. But this planet wouldn't be here. You wouldn't have a water planet if water acted like everybody else. Because at this temperature right here, there's no way you would have liquid water. It wouldn't happen. It'd all be a gas. There'd be no liquid water. You couldn't do this. If it weren't for hydrogen bonding, you couldn't do that. There wouldn't be any liquid water. And water, over a long range of temperatures, can be a liquid, can't it? 0 all the way to 100, that's pretty good. But once it gets to 100, even that kind of breaks some of the hydrogen bonds more and more, and then it's free to boil like that. Well, let's go down here, and let's look at this picture down here. And it's called, it's called solution, but we're making a solution. What if I put some sodium chloride in water? Why is it that water is so good at dissolving? Okay, here we go. Number one, this is an ionic compound, right? What are ionic compounds made of before you put them in water? Yes, be a little more specific. Yes, ions, right? And so, right here, this is the chloride ion. He's minus charged. And here's the sodium ion. He's positively charged. And chlorine ion, chloride, sodium. Anyway, I have a bunch of ions, right? The only thing to keep them together is their attraction to each other. Plus, minus, plus, minus, plus, minus, plus, minus. See that? That's an ionic compound. How together ionic bonds between ions. Okay, now, you put it in water, and the water says, I'm going to dissolve you. Who are you? What do you mean? You can't take me apart. Oh, well, but look at me. Look right here. This part of the water molecule is slightly positive. And I'm going to be attracted to that negative ion, aren't I? Okay, now I'm attracted. You didn't touch me. Even though I've never seen the number, I've never seen the real number, another water molecule, another one's attracted, another one, another. I've never seen the actual number. How many water molecules does it take to pull that chloride ion out? Now, how do you pull it out? Watch here, ready? Attraction, 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 water. Attraction, attraction, attraction. The water's attraction has to overcome what? The attraction between water and chloride ion has to be greater than chloride to what else? Sodium. You know what? That doesn't always happen. If you look at the solubility chart, look right here. Look at the solubility chart. Hey, sodium chloride. Sodium chloride, what does it say? Soluble. What does that mean? You put me in water, water's ability to take you apart is greater than your ability to stay together. Let's take another one. Let's pick silver chloride. Look at silver chloride. Silver chloride, what does it say? Insoluble. What? I'm putting you in water. I'm putting you some silver chloride in water. Well, go ahead. What's going to happen? It won't dissolve. Silver chloride's ability to keep itself together, attracted, is stronger than water's ability to take it apart. That's how that works now. Now let's go down here now. This is called solvation, not salvation, but solvation. And what happens is, what do you think is going to happen to the sodium ions? What part of the water molecule will be attracted to the positive sodium ion? The oxygen end. And that's why that picture, look at the picture shows. See? The picture shows hydrogen end being attracted to the chloride ion. And here, it shows what? It shows the oxygen end being, see that? And so what you can do is, if you keep taking it apart, you can actually, quote, dissolve this thing, can't you? And it's still there. The ions are still there. They're just so spread out that we have made a solution, have we? It's called in solution. I'm going to show you one more, and then that'll be enough for today. But you know what? There's something else very famous that you've heard of that also produces hydrogen bonding. Okay, now, later in the year, we'll do a organic chemistry. And I will teach you all this, but if you gave me a carbon compound, and the carbon compound had one of these OHs on there, now that's different than inorganic chemistry, because inorganic chemistry is like this. Here, sodium hydroxide, ready? What is that made of? It's made of one of these, and it's made of one of these. And they come apart in the water, don't they? That's why it's a base. But in the organic world, that carbon attached to OH, you're not leaving me. I'm not made of ions. Put me in water. That OH is not coming off. It's not an ion, is it? So when you have that COH, you have a thing called an alcohol. Now, what happens when O and H start to make a bond to each other? What is that? What's that old story again? Even sharing? Polar covalent, isn't it? So alcohols will also have one part of it, which will be slightly positive and one will be slightly negative. So, do alcohols dissolve in water? Yes. I have a bottle over there. It says 70% rubbing alcohol. Well, what's the other 30%? Then it does mix, doesn't it? And so likes dissolve likes. If you're polar and water's polar, I'm going to tend to dissolve you. What if I'm polar and you're ionic? Well, that's kind of plus minus, isn't it? I'm kind of plus minus. You're kind of plus minus. Polar things dissolve ionics, don't they? Polar things dissolve other polar molecules. Likes dissolve likes. Yes?
So, I noticed the molecular formula you have is CH3CH2OH, so you don't write C2H5.
Okay, now,
Is it because the OH
this is the way you would do it for somebody who didn't care about organic chemistry. Organic chemistry, and I'll teach this to you, they want to write it so you can see the structure.
Okay.
CH3, do, 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 do. CH2, do, do, OH. See? So what they want to do is they want to draw it so you can see the structure. Now, we'll do that later. I think it's fun. When I get to organic, I think you'll enjoy that quite a bit. But what I want to show you is this OH group is not an ion to begin with. So when I put it in water, it's not coming off. Alcohol is not polar. I'm sorry. It's not ionic. My fault. It's not ionic, but it is polar, isn't it? Okay, go ahead, Tim.
I was just gonna say, I was looking at how many water molecules it takes
How do you come up with that number?
I, looked it up and
If you could find that in writing somewhere, I would have said it would take a lot more than that. But if you could find that somewhere, I'd love to see that number. Yeah, I'd love to see that. Okay. Okay, there's something. All right. Tomorrow, we'll probably review this real quickly, but I do want to get a little bit, finish this lesson here and then go on to some other stuff.
So does this make covalent or ionic bonds stronger? Because I was reading about ATP and I noticed that they talked about the phosphate bonds breaking.
That would be a covalent bond.
Right. So does that? But they said that the terminal one was specifically weaker than the other one. Does that,
That's a good question.
Can some elements be, some bonds be stronger or weaker than the others?
Yes. So the people who study organic chemistry, for example, they'll say, hey, I want to attack that thing. I want to attack that molecule and turn it into another molecule. Well, what's the weakest, where are the weakest bonds here? And they actually know that. They actually know that like double bonds can be attacked. And because they love to turn it back to the single bonds. Organic chemists actually do that, say, we want it to go here. Okay, and so they do all kinds of fancy things, like they'll use UV light, they'll do something to make that the spot where it attaches. But I agree with you. There are some places where it would be a weaker bond, but it doesn't mean it's going to come off.
Okay.
It would take a lot to take the OH off of an alcohol.
So did you say it's circumstantial for each bond? About whether or not it's
Based on the structure, yes.
Okay.
I'd say, and I haven't studied the phosphate bonds in that as far as. I know they're high energy bonds.
Yeah.
They're very high energy
Yeah,
bonds.
that's why they're used.
But it seems to be easy to take the end one off before, like that. You're going to find out, even in atoms, there's some atoms where taking the first electron off is easier than the second. Like sodium, if I take one off, it's not that hard. But now I only have 10, 2 in the first, 8 in the second. You have to jump it way up because I have 8 in my outermost energy level, and you're trying to take one of those. Try it. It's going to be very hard. So just like each atom has an electron, it can be harder. Each bond can be that way too. Gotcha. Thank you.
I have a question.
Okay.
So I don't know how C6H6 is miscible with C6.
Ooh, you know that word miscible? Look at that, I'm impressed. Miscible. Miscible means it dissolves in it. You've been doing your homework. Wow, whoa, how do you know this? Who's been telling you that? Who's been showing you that?
YouTube. Because I was
Okay, wait,
curious.
hang on. Now what you have to do is,
This one has
this is called benzene, okay?
yes.
Now, benzene, 2, 1, 2, 1, 2. You did, how do you know this? Good. Man, I'm impressed. You have that in your mind, your vision of this?
I kind of remember it, but this has to, because of the periodic table, this has to have
Wow, I'm impressed.
I just didn't know how to draw this
Okay.
miscible with
Okay.
C. I forgot. I know it starts with a C.
Hexane?
Yeah.
Hexane. This is called benzene.
I just have to tell him I won't be here tomorrow, so he'll just.
yeah.
Now, I will tell you that in almost every case, if you're only made of carbon and hydrogen, the bonds are so even that these are not going to dissolve in water, neither one of them. See, when you have only carbon and
But-
hydrogen, neither one of them is going to dissolve in water.
But it was that these are these miscible within each other.
Oh,
Not in
okay,
water.
now that's different.
I didn't know how
That's
to.
different.
I
Okay,
didn't know how to
because-
show that.
Non-polar,
Non-polar.
non-polar. And likes dissolve likes. So I would say non-polar things would tend to dissolve in non-polar things.
Was there a way to draw that? How like, because like in this one, it
It-
shows how.
Yeah,
the,
what I'm
the
doing, yeah,
water
okay.
Will
I-
bond with.
Because we don't have a whole class just on bonding, the most I can tell you right now is water and alcohols are the two polar molecules we'll talk about. And when we get back to these old pages back here, I'll show you tomorrow how to take any molecule and try to figure it out. if you can. This is much more complicated. This is very complicated, what you're doing there, to try to figure out the, what is polar, but,
Mr.
yes,
Just really quick, tomorrow, I don't know if my band teacher has told you yet, but we're
yeah,
gonna
I
be
did read,
playing
I read that.
on the
Yeah, okay.
thing. So I'm gonna miss this.
Oh, wait, I should turn this off.